pick up where we left off yesterday. Okay, I think today's going to go a little bit better because we're going to get into some examples. Okay, and that's when it usually clicks for us. Okay, but we'll get there in a second. Let's see. Mario. What page, Mario, is that one on?
105.
105. Number 8?
Yeah.
Okay, so looking at page 105, number 8, the directions say to determine if it's even, odd, or neither. So we have to plug in negative x, okay, the opposite of some x value we choose, and we're going to see what we get out. Do we get out the same function, the opposite function, or that mixture idea where it would be neither even or odd? So if we plug in negative x, let's see, so this would be negative 3x if we multiplied those together. If we simplify negative x cubed, negative times negative times negative is a negative. Notice how we're subtracting it, so that would change to a plus. Down below, though, we have absolute values. So we know this would end up being a negative x cubed, but if you're taking the absolute value of it, it would then change to a positive x cubed. All right, so take a look at what you get when you plug in negative x and compare it to the original. Exact opposite, exact same, or mixture. What do you think? How do you know?
Because all the terms are opposite, like 3x changed to negative 3x.
Okay, so this one changed.
And then negative 8x cubed changed to positive 8x cubed.
Right.
And the bottom stayed the same.
But the bottom stayed the same. That's what's a little tricky, right? Okay. So it looks like just the top numbers changed, but the bottom one didn't. We have to be a little careful with this one because it's a fraction. And the other ones on there weren't fractions. But this one, let's think about this for a second. If I were to write this fraction, and I were to write that fraction, and I were to write that fraction, are those all different values? Aren't they all negative 1/2? They look different, right? But they're all the same value. So when it comes to a fraction, it doesn't matter really where the negative is or where the opposite is, as long as it's only up top, only down below, or only out front. Does that make sense? Okay, so when it comes to analyzing this fraction, we said only the top was opposite, right? Not the bottom. So what you can think about doing is, if the top's changed, couldn't you pull that negative from the top out front? I mean, we said these are the same value, right? So if you pulled a negative out of the top, this would then change to a positive, that would then change to a negative, and the bottom would still stay the same. So take a look at that. You have the opposite of what now looks like the original function, right? The one you started with. So at first glance, it looks like it might be neither because the bottom term did not change. But since we're dealing with a fraction, we kind of got to be careful on negative components of a fraction, where they might be found. Does that make sense? Mario, does that help a little bit? Okay, so that one was a little tricky, but just because it was a fraction. Are there any other homework ones you guys want to go over before we check out some inverse examples today? Another one, Mario? Yeah?
106.
Okay. Which? 13. All right. Determine if we are even or odd. Okay, so same type of question, just instead of looking at an equation to test, we now have to look at a table to test. So, pick a point in that table that you want to kind of focus on. Doesn't really matter which one. Mario, can you pick one for us? The first one? Okay. So let's say that this is a point that you know is on the graph. Okay, you know that's there because it's in the table. If you were to plug in the opposite x, what would you get out? So based off the table, if you were to plug in the opposite of -7, which would be +7, right? Would you get out the same y value as the original point? Would you get out the opposite y value as the original point? Or would you get out something completely different? You see how that's the same concept of the function? You either get out the same function, the opposite, or something completely different. Okay, so if we plug in the opposite x, looks like we get out the opposite y. So how can we classify that function? Even, odd, neither. Yeah, it'd be odd. Good. Okay, now it says give a reason for your answer, so you might have to write a little sentence describing that idea, but at least you're able to classify it. Is that okay, Mario? Okay, so the other two tables are very similar. You have to pick a point you want to start with and then test to see if you plug in the opposite x, what happens to the y value. Is it the same, is it the opposite, or is it that neither idea? Yeah?
So if it's the same, it'd be even.
It'd be even. All right, so let's take a look at 14. If you pick the first one, okay, plug in the opposite x, you would get a +4. And notice how when you plug in +4, you get out the same y value as the point that you originally picked. So you plug in the opposite, you get out the same. That's the concept of an even function, that y-axis symmetry. Okay? I think I'll leave the last one for you guys. You can try that one. Any other homework ones? All right, let's check out some inverses today. We did a lot of definitions yesterday and a lot of like concept writing, things to look for to help us analyze if we have a one-to-one function or an inverse. So I know yesterday probably didn't sink in too much because we didn't go over many examples or visuals for you to see, but that's what we're going to do today. We filled out this top chunk yesterday, so you're not going to have room to write these in, but I'm just going to paraphrase some concepts that we talked about yesterday. Okay, so we defined what a function was, we defined what one-to-one meant, and we defined what an inverse was. Okay, so before we tackle some of these examples, let's make sure we're good with these definitions. Okay, from yesterday, what did we say a function was, or how can you think about what a function is, maybe a characteristic you can look for? Yeah? Each x has only one y. So in terms of a table or a graph, if you're looking at those representations, you don't want to have any repeating x's. Because if you have repeating x's, that means you have more than one y value associated with it. So for a function, we want no repeating x's, meaning for every x there's only one y. What about a one-to-one function? It's kind of similar to what a basic function is, just switched. So Gary said a function is for every x there's one y. If we switch that idea, if we switch that concept, yeah?
There's no repeating y's.
There'd be no repeating y values, meaning for every y there's only one x. Okay, so no repeating y's. Okay, so basic understanding from yesterday, we have those two definitions we can think of. What did we define an inverse to be? Maybe you got to switch to the front because this is definitely a new vocab word for us. An inverse is the basic idea of, yeah?
You switch the x and y values.
You switch x and y values. Okay. Now, yesterday, at the bottom of page 107, we went through kind of a critical thinking process for us to analyze when an inverse exists and when it doesn't exist. Remember doing that? Can we reference page 107 for a second at the bottom? Okay, if we look at those few sentences we wrote, we initially determined that if a function is not one-to-one, that means it has repeating y values. So if you apply an inverse, if you switch the x's and y's, those repeating y's then become repeating x's, which is a problem for the inverse, because if you have repeating x's, that means the inverse is not going to be a function. So in order for an inverse to be a function, the original equation, whatever we start with, must be one-to-one. So we're going to focus on that idea today. We're going to determine when does an inverse exist, when does it not, and if it does exist, we're actually going to find it. Okay, we're actually going to switch the x and y values. So big idea, for an inverse to exist, f of x must be one-to-one. Okay, we wrote that down yesterday on page 107 at the bottom. For an inverse to exist, the original function must be one-to-one. So we have to check that first before all else. Okay, so did we mention the notation yesterday, f of -1? F to the negative first power? I think we did. We just didn't get to any examples, right? The bell rang. Okay, so let's just take a look at the table. We need to first determine, is this function, based off the table they give us, one-to-one? If it is, we should be able to find an inverse. If it's not, we know the inverse doesn't exist, meaning it's not going to be a function. So let's see which way this goes. Can you determine if this table is one-to-one or not? What do you think? Is it one-to-one? Is it not? How do you know? Maybe think of these key concepts that I kind of jotted down from yesterday. Yeah?
It's not, because there's 2 repeats in the table.
There we go. We have a repeating y value, okay? And we said a one-to-one has no repeating y values. So if you have repeating y values, you're not one-to-one. We'll say f of x is not one-to-one because there are repeating y's. Okay, specifically that number of 2. Therefore, since we know it's not one-to-one, okay, since it's not one-to-one, we know the inverse does not exist. If we were to switch the x's and y's, it would not be a function. And I hope that makes sense, because if these 2 y values then become x values, these would be repeating x's. Okay, so we'll say, so the inverse, that notation, f to the negative first power, does not exist. Meaning it's not a function. So since the inverse doesn't exist, we're not actually going to go about finding it. There's no point to doing that, because if you plug one number in, you're going to get more than one number out. Not a function, not worth it. Let's go ahead and try B, okay? Based off of this table, can we determine if the original equation or function is one-to-one? What do you think? Do you have any repeating y values? No. Okay, so f of x is one-to-one because there are no repeating y's. So that means the inverse does exist. Okay, we should be able to switch the x and y values and develop a new function, something that would have no repeating x's. So since we know that an inverse does exist, we're going to try to find it. Okay, we're going to develop a new table to represent what the inverse would look like. If we were to switch the x's and the y's, what would the table look like now? So it looks like we have 1, 2, 3, 4, we have 5 ordered pairs. And since this table is going to represent an inverse, we're going to make sure we use the correct notation. Okay, f to the negative first power. So if you were to apply an inverse, if you were to switch the x and y values, can we think about what the inverse table would look like? Maybe we'll start with the first ordered pair, -1, 6. If you were to switch the x and the y, what would the first ordered pair look like in the inverse table? Go ahead, Kyle. 6, -1. Yep. So nothing's becoming negative. Nothing's becoming the opposite. You're simply switching the values. If you continue through the rest of the table, I think we can do that. Simply switching the values. Okay, so if this is the original function based off the table, this is what the inverse function would look like by simply switching the points. Do you think we could do that? Simple idea, right? Okay, don't overthink it. Inverse is just switching x's and y's. All right, so those were two graphical table examples. If we had a function that was not 1-to-1, or if we had a function that was 1-to-1. Let's go ahead and try a graph. Okay, so graphically speaking, how can we determine if this function is 1-to-1? How can we determine if there are no repeating y values? Yeah? We're going to do a horizontal. Okay, so we use a vertical line test to determine if a graph's a function. We're using a horizontal line test, though, to determine if it's a 1-to-1 function. So if you were to drag your pencil horizontally going up and down across that graph, would your pencil touch once every single time? Sure looks like it. Okay, so f of x is 1-to-1 because we'll say it passes the horizontal line test. All right, so since it's 1-to-1, that means that we can figure out what the inverse looks like. If we were to switch the x and y values, okay, what would the new function be? So instead of switching table values like we did before, we're going to have to switch ordered pair values because that's what shows up on a graph. So this first ordered pair right here is -5, +5. So if you switch those numbers, your new point would be at 5, -5. So you take an original point from the graph, and when you switch the values, you get the inverse point. You can plot where that would be. Okay, we're going to continue through the other ordered pairs. So the next one is -2, 1. If you switch those, you get 1, -2. The next ordered pair, 2, -1, switch those. -1, 2. And the last one, 4, -4, switch them. We get -4, 4. So if we connect the dots in straight lines like what was used before, okay, that is our inverse graph, our inverse function. So let's go ahead and label it appropriately. We would say this is f to the -1st. Are we still okay with that idea? Switching x's and y's. That's all we're doing. It's just a little different each time depending on what we're given, either a table or a graph. We'll get to the equation part in a second. I want to pay close attention to this one a little bit more though. Can you describe what type of symmetry might be going on with these graphs? What can you do to the black graph that would give you the blue one? Okay, we talked about 4 different types of symmetry. You can fold it across the y-axis, you can fold it across the x-axis, you can fold it diagonally, or you can rotate your graph upside down. Can we kind of pinpoint what's going on here? What do you think, Kyle?
X-Y symmetry?
Okay, so the diagonal. Let's go ahead and check that out. Gary, is that what you're going to say, or are you going to say something different?
Yeah, I was going to say that.
You're going to say that one? Okay. This might be a little bit hard to visualize. I'm going to try my best to help us see it. If you were to take this original black graph and fold it over that diagonal line, would you notice that the black section would land up on this blue section on the other side? Can you visualize that? Okay, and doing the same thing the other way, if you were to take this black section and fold it over, it would land on top of this blue section. Okay, so we do have that diagonal symmetry. So even functions, we said, represented y-axis symmetry. Odd functions, we said, represented origin symmetry, that rotational idea. But now we have these inverse functions, which represent the diagonal symmetry. Okay, so they have different connections depending on which type of function you're working with. Really, really good. Okay, let's check out the next one. Does that graph, or is that graph of g of x 1 to 1? You're shaking your head no. Why? It touches what? It touches at 0 twice. Okay, so there's one spot where it doesn't pass the horizontal line test. Okay, it actually touches 3 times if you go a little higher. Okay, but you just need one spot where it doesn't work. So we can say g of x is not 1 to 1 because it fails the horizontal line test. So since g of x is not 1 to 1, we could say the inverse, okay, g to the negative first, does not exist, meaning it's not a function. You could switch the x's and y's. There's nothing stopping you from doing that, but if you were to do that, the graph you would get would not be a function. Okay, it wouldn't pass the vertical line test. So we're not actually going to go through that process. Okay, the inverse doesn't exist, meaning it's not a function. Good job. Okay. Is it starting to sink in a little bit? I know yesterday was all words. I think the examples help. Let's try another graph. All right, what about h of x? Is that graph 1 to 1? See the head shaking? Yes, good. Okay, so h of x is 1 to 1 because it passes the horizontal line test. So that must mean the inverse does exist. It is a function. We should be able to switch the x's and y's. Okay, so going through our ordered pairs again, our first one is -5, -3. We'll switch those values to get our inverse point, and we'll go through all the other ones. Next one is -4, ½ so switch those. Next ordered pair is -3, 3. So we can switch those. And the last one, -1, 5. Switch them. We get 5, -1. And we'll play connect the dots. So if that's our inverse, that's what we get when we switch the x's and y's. We're going to label it appropriately. This would be h to the -1st power, just because the original one was named h. Does it look like that graph has the diagonal symmetry? Yeah, if you were to take the black one, fold it diagonally, wouldn't it land on the red one? Okay, so inverses have that diagonal symmetry to them. All right, so I think we're doing good on tables. I think we're doing good on graphs. Let's go ahead and try equations. This is when it gets a little tricky in terms of a mind game. Okay, these are the thinkers. All right, so we need to determine if this equation is 1 to 1. So let's think about what type of equation we're working with. Can you give me the name of that equation? Is there something in there that's kind of cluing you into the type of function we have? Yeah.
Is it quadratic?
It's a quadratic. So if you were to graph a quadratic, what shape would it look like? We're going to turn an equation into a graph. That way we can use the horizontal line test. Yeah.
It'd be a U.
It'd be a U shape, okay, a parabola. So since this is quadratic, we know it's a U shape. If you were to apply the horizontal line test to the U, would it pass? No, because you would touch twice, right? All right. So f of x is not 1-to-1 because the graph fails or doesn't pass, whatever wording you want to use, the horizontal line test. Therefore, we know the inverse doesn't exist. If we were to switch all of those ordered pairs on the graph, we would no longer be able to use the vertical line test. It wouldn't be a function. All right, let's try another one. What type of function do we have in part G? Can you name it? Yeah. Linear. So if you graph it, what would it look like?
Straight line.
Straight line. Might have some slope to it, sure. Okay, straight line. Does that straight line pass the horizontal line test? Sure does. F of x is 1-to-1 because the graph passes the horizontal line test. All right, so that means we should be able to find an inverse, and we're actually going to do that. Okay, we're actually going to switch the x's and y's and see what happens. But since we're given an equation, it's not like we have ordered pairs or points to switch. We actually have variables to switch in this case. And f of x we know is the same thing as y. So if you were to take this equation and switch the x and y variables, it would now look like x equals 2/5 y minus 3. The issue for us, though, is we're not used to seeing x equals equations. We're used to y equals. So what we're going to do, just for visual sake, so that we don't get too confused or too worried, is solve this equation for y. So you might need to use some algebra to help you do that. How can we get the y variable all by itself? Yeah.
You gotta add the 3 over.
Add the 3, okay. You want to keep going?
Yeah. And then multiply by the reciprocal of 3/5.
All right, so multiply the fraction, or divide the fraction over by multiplying by the reciprocal, same concept. So that would get the y by itself, and maybe we can distribute in that 5/2. We'd have 5/2 x plus 15/2. So this is the result we get when we switch the x's and y's. So we need to label this as the inverse. So this would look like f to the negative first. Just like we labeled the table, just like we labeled the graph, we're going to label the equation too. All right, let's try the next one. Can you tell me what type of function g is? G of x? Can you give me the name? Good, Kyle? Square root. So what does a square root graph look like? Half of a parabola on its side. All right, so something like that. If you were to use a horizontal line test, would that graph pass it? Only touch once? Okay, so g of x is 1-to-1 because the graph passes the horizontal line test. Therefore, we know we have a function, or not a function, an inverse that is a function, and we're going to go ahead and try to figure out what it is. So we need to switch the x's and y's. Okay, g of x is the same thing as y. So if we switch the variables, we now have x equals 2 times the square root of y plus 3 and then plus 4. But again, we're not used to seeing an x equals equation. We're used to seeing a y equals. So how can we get that y variable all by itself? Can we start to move some things over? We have a lot to move over, but we got to start somewhere. Yeah.
Subtract 4 from both sides.
All right, subtract 4. So far, so good. What's next? Good, Kyle?
Divide by 2.
Divide the 2. Now, when you divide the 2 over, you have to divide both pieces by 2. So, x divided by 2, you can maybe leave it like that. If you divide 4 by 2, that simplifies to 2. All right, keep going. Almost there. Yeah?
Square both sides.
Square both sides. All right, so if we square the left-hand side, okay, all of those would be in a parenthesis being squared. And if we square the entire right-hand side, that will cancel out the square root. Last but not least, get the y by itself. We think and subtract 3. Is that what you say? Yeah, okay. So x over 2 minus 2, that whole thing squared, minus 3. We got the y by itself, meaning we found the inverse, so we're going to label it appropriately. This would be g to the negative first, just because the original function was called g. All right, and we'll leave it like that. We switched the variables and solved for y. Our result represents the inverse. We doing okay? All right. We're going to save that back page for tomorrow. I want to, though, take a look at your homework for a second on page 112. Okay, I'm going to give you some clues or hints to help you on this back page. Okay, so if you take a look at the top, it says for problems 5 to 8, use a graphing calculator to draw a rough sketch. Okay, so I know that, we have class time now to go over this, but let's just say we didn't have this opportunity to talk about this section together. If you ever have to use a graphing calculator at home and you don't have your own personal one, there's a really cool website that you can visit called Desmos.com. Are we familiar with that? A little bit? Some of us maybe? Desmos.com/calculator. You can type or graph anything. I see smiles. Are we familiar with this? A little bit, yeah? Do you guys know something that I don't know? Like an inside joke? No? Okay. So, Desmos.com/calculator, you can go online and graph any equation you want. Okay? But that's just for future purposes if you don't have one of your own. What we're going to do, maybe some of you want to grab a calculator and kind of follow along, because I know it's been a while since we've used these calculators. We're going to go ahead and graph these functions. Okay, so if we look at the directions, it says using a graphing calculator, draw a rough sketch of the graph that's given to you. Then determine if the function is one-to-one or not. Okay, explaining how you know. And then if the function is one-to-one, find the equation of the inverse. Okay, this is basically what we did on the last 3 examples with those equations. Okay, we're going to apply it to this homework. Show all of your work and use complete sentences for everything. Okay, so what we're going to do is we're going to graph this on our calculator. Maybe some of you might already know what it's going to look like. Not sure, that's why we're going to test it. Okay, how do we graph on our calculator? It's been a while. Remember, yeah. Y equals. Okay, so clear out anything that's in there. We're going to go ahead and type in the equation. You got to be careful though, because it is a fraction. You got to put the whole top in parentheses and the whole bottom in parentheses. Because we're taking the entire top divided by the entire bottom. Now before you hit graph, let's go ahead and change our window. They don't really give us any clues as to which window to use. So if that's the case, I always go in tens in every direction, negatively and positively, and I count by ones. This is just my personal kind of starting point, and if that doesn't work well, you can always go back and change it. Okay, so let's change our window to those tens. So with the equation in and the window set, you can go ahead and hit graph. Okay, so just copy down a rough sketch of what's on your screen. Now we're not actually going to go through the rest of the directions because I think you guys should be able to do that or reason yourself through it, but based off of that graph, could you determine if it's 1-to-1 or not? Alright, and based off of that analysis, couldn't you figure out what the inverse is, perhaps? Okay, so I'm going to leave that up to you, but now that you have the graph, you guys should be able to proceed through these questions. Okay, let's go ahead and try the next one. We'll go back to y equals, we'll clear out whatever's in there, and we'll type in the equation to graph it. To get your powers, you have to use that caret button above the division button. Go ahead and hit graph. Alright, so there's a rough sketch. You should be able to determine if that's 1-to-1 or not. And then proceed from there. Let's check out the next one. Another fraction, so whole top in parentheses divided by whole bottom. This one's a little weird. Can you guys visualize the asymptotes in there? I know we haven't really talked about them much. We'll definitely be getting into asymptotes later this year. But do you realize how that graph is getting close to some places but not crossing it? Okay, so we could probably draw those in. Alright, so based off that graph, you should be able to determine if it's 1-to-1 or not, and then go from there. Let's see, the last graph, we should already know what that shape is, but we'll get a rough picture of it anyway. Alright, so you can determine if that's 1-to-1 or not. Do you guys think you can go from there? Yeah? Okay, so calculator might be necessary just for us to get a visual of the graph, at least for equations that we're not too sure of what they necessarily look like. Okay, but based off those graphs you can determine if it's 1-to-1 and therefore if a function exists or not. Okay? So you guys should be good on that page, and I think you should be pretty good on the front too. Okay, we still have a little bit more to do tomorrow, just that back page. It's not going to take the whole day tomorrow, so you will have some time to work on your homework. Okay, just a reminder, we are getting towards the end of a unit. This is actually our last section. So next week we have that partner quiz on Tuesday, bless you, and unit test Thursday, Friday. Okay, just an FYI.